this conference. Thank you, organizers, and also thank you for chair. Today I'm going to discuss quantum invariance and Kashaev volume conjecture. But I think this topic is not familiar to most of the audience. So I will introduce many things and then briefly add new results. So today I will discuss those three topics. First one is quantum invariance. And so as an example of quantum invariance, I will define Kashaev invariant. And then second, I will discuss volume conjecture a little bit. And then I will discuss optimistic limit. And I will show why optimistic limit is very natural according to the volume conjecture. So I will start. So first, quantum invariance. So for given two link are equivalent if and only this diagram is related by finite steps of Reidemeister move. So I think you already know all Reidemeister move. So first Reidemeister move is this one. We change this way. Second Reidemeister move is like this. And third Reidemeister move is this one goes like this. So this third one, actually this third one is the starting point of quantum invariance. So this one is related to Yang-Baxter equation. So I will define it soon. Definition. Consider Vn as L-dimensional vector space. The field is complex number, and consider isomorphism. R. This one comes from tensor product of Vn to the tensor product of Vn. This R map is called R matrix. If it satisfies Yang-Baxter equation. And Yang-Baxter equation is defined by this way. R tensor identity, composite, identity tensor R, composite, R tensor identity equal, identity tensor R, composite, R tensor identity, composite, identity tensor R. So this equation is called Yang-Baxter equation, and the solution of this Yang-Baxter equation is called R matrix. In here, identity is identity. From Vn to Vn. So the important fact is that this
from Vn to Vn?
R is Vn tensor Vn. So it is multilinear map if I know NOP of Vn tensor Vn. So actually I will associate R matrix to this diagram, and it has two strings. So that's the reason we consider tensor product. Proposition. So this R matrix determines a link invariant. So there's a way to define link invariant from R matrix. So I will show you idea. Consider those diagrams. for this diagram, we assign R. And for this diagram, we assign inverse. We assume R is an isomorphism, so we can consider R inverse. And then for those usual string, we assign identity. And then we define several more maps that is called two local minimum and two local maximum. So those two, not this way. So about those two local minimum, we define certain map that comes from C to Vn tensor Vn. For those two cases, we define map from Vn tensor Vn to C. So we have to define those ones. So we define map satisfying certain conditions. I will denote the condition star and show some of the conditions. So those diagrams are actually called elementary rectangle diagram. These crossings and those straight lines and two local maximum, two local minimum, those are called elementary rectangle diagram. And we define operations. We have two operations on elementary rectangle diagrams. One is composite and the other is tensor product. So composite means that for two elementary rectangle diagrams, we define composite just by stacking them vertically. And tensor product is so stacking them horizontally. Then I will explain the condition. So we for elementary rectangle diagram we assign maps and we define certain functions for those local maximum and local minimum. And everything should satisfy those conditions. It has more than 10 conditions, and I will draw only few. For example, this diagram should be this one. If I write this one as map, then R composite R inverse equal identity tensor identity. And so if we define R inverse for we assign R inverse to negative crossing, and then this condition satisfies naturally. And there's many other conditions. For example, for writing as a third group, and consider those orientation. This one actually satisfies from Yang-Box equation. And so if we choose I matrix and assign R to each positive crossing, and then this condition also satisfies trivially. And there's actually many non-trivial conditions. First one is this one. To guarantee this condition, we need certain restriction for the map. So if I express this one as an equation, this one means that identity tensor this map, so it means this above this stage, and then composite those map tensor identity or identity. So we have to define those map satisfying this condition. So it's kind of restriction, and also we need lots of conditions. one example is this one. This one should coincide with this diagram. I can express it by equation, but it will really complicate. Anyway, so and more, many more. And so for fixed, so usually finding R matrix is difficult. But if we have R matrix, and then usually, not all the time I guess, but most of the cases, we can define those maps, satisfy all the conditions. But actually, that one is not proposition, so maybe it is not proposition, but main 2. So, but for important R matrices, we can always find those curve map and CAD matrix. So, assume we have R matrix and we define those maps properly. And then from the link diagram, we can define link invariant. So consider link diagram of N, link diagram D of N. And then from here, we can split the link diagram to element rectangle diagrams, and then we can make those, we can consider a map, and the result becomes a map from complex number to complex number. And we have to be careful that for sometimes we have those kind of crossings, and in this case, so we cannot assign R here because R is assigned to here, but we can rotate this one using the local maximum and minimum. Consider those diagrams. And then instead of using this one, we rotate the crossing a little bit and then use the standard R matrix and composite with certain local maximum minimum. And so using those methods, we can always define certain map from link diagram. And then for one, we can consider this one. This value, this is complex value, and this one is a link invariant. And usually this value is called quantum invariance. So this is very simple way of, there's actually, usually quantum invariance comes from representation theory of quantum group and very complicated algebraic structure, but simply speaking, this one is quantum invariant, and we can usually obtain quantum invariance using this method. So today I'm going to discuss Kashaev invariant and Boole conjecture. So I will introduce you Kashaev invariant. So Kashaev invariant is quantum invariant. Fixed an integer, fixed bigger than 2, and then we define Q as nth root of unity, and I will use index set, and also use certain coefficient that is n bar is the element of I, and this one is the residue of n modulo capital N. And I will define set ijkl equal 1 if for indices ijkl, we define zeta like that way. And then for x, for a complex number, we define xn as 1 minus x, 1 minus x squared, 1 minus x, and bar. And so usually for as root of unity q, we will usually use those two values, qn and q inverse n. And these two numbers are called quantum integers. But these are named integers because they satisfy many properties of integers. Now we fix a basis of the n. E1 till En. So from now on, we will only consider those capital N dimensional vector space Vn, and then fix basis always from En to E1 to En, and then we can express the I matrix using those bases are the K tensor, the L. Using standard notation, we can express it like KL, IJ, EI tensor, EJ. And for those commap, the K tensor, EL. This one, we use those notation. This one is also coefficient. This one is complex number. So it's a kind of misuse of diagram. I think you can understand what it means. And then in this case, for 1, IJ and EI tensor EJ. But these are all coefficient. Those are just complex numbers. And then Kashaev R matrix is defined by this way. So I will use those coefficients IJKL equal n times q minus 1 over 2 plus I minus k over those quantum integer of yours, I minus j bar, q inverse, j minus l bar, q L minus K minus 1 bar, the inverse K minus I bar, and then we multiply by zeta ij Kl. So it is proved that this matrix satisfies Yang-Baxter equation. So this is R matrix. And then for local maximum and minimum, the map goes like this. This coefficient becomes minus 1 over q to the minus 1 over 2, k plus 1 L, and for this map, ij, this one becomes minus q minus 1 over 2, and delta I minus 1, 0. So this delta is Kronecker delta. If those two numbers coincide, then it is 1, and if not, then it is 0. And for other cases, this one, and for other orientation, not this one. For other case, KL, it is just Kronecker delta. IJ, in this case, just Kronecker delta. And then it is proof that those maps satisfy all the conditions. And so we can define link invariant using those informations. And the result is called Kashaev invariant. And it is denoted by n. This one is just complex number. It is not a polynomial, it is number. And it depends on capital N. So L is the link diagram. So although definition is simple, it is hard to see what Kashaev invariant is. So I will show you a way of calculation. So consider figure A now. And then orientation goes like this. And then assign variables for each edges. I will assign I1, I2, I2, I3, I4, I5. So I1 is until here, I2 is until here, and I3 is between two crossings. So we assign variables to each side, each edges, and then I4, I5, I6, I7, I8, I9, I10, I11. And then, so we assign variables to each side of diagrams. And then the Kashaev invariant of figure A naught is expressed like this way. So those variables changes for all possible indices. So it will be very huge. And then for this crossing, it is certain I matrix. The form looks like I10, I11, I6, I8. And then for second crossing, it gives the value becomes I8, I9, I7, I4. So for crossing, we see the variables of edges and then just product all those coefficients. And then for third crossing, we have I6, I7, I5, I3, and then for last crossing, we assign I3, I4, I1, I2. And we have extra terms. So those extra terms comes from the local maximum and minimum. And so it is very complicated, but if you follow the calculation very carefully, and then it is known that the result becomes in a very simple form. Qi, Q inverse R. That is the Kashaev invariant of figure in that. It is a number. there's a very famous theorem by two Murakami, Hitoshi Murakami and Jun Murakami, that for link, this Kashaev invariant is actually coincide with the convergence polynomial evaluated at nth root of unity.
So, unity is Q is an nth root unity.
Yeah, Q is nth root of unity. So, where J and T, this one is nth convergence polynomial. So I will do not explain the definition of convergence polynomial. But roughly this one means that nth convergence polynomial means for link we make the diagonal into n-1 parallel copies. So it becomes really difficult link, and then calculate the joins. And then if we modify a little bit, and then that becomes nth convergence polynomial. And so actually convergence polynomial is more popular than Kashaev invariant. After their result, usually people concentrate on convergence polynomial. So this one is very hard to see, but convergence polynomial, there's many interpretations of them, so people usually focus on here. But today I will focus on Kashaev invariant.
And there is for every link or only
For every link. But yeah, today I do not want to go precisely, so I will lie in some places, and so actually for writing this way we have to be a little careful. But anyway, it is, roughly speaking, this one is correct. Then now I will go to Boole conjecture. Section 2. So for a hyperbolic link, Boole conjecture is like this. N goes to infinity, n over to pi, log n. So this is conjecture. Volume L over I times CSR. I after T goes for rather pi square. And then where this one is hyperbolic volume of L, and CSL is Chern-Simons invariant defined by pi square. In here we need minus 1, square root minus 1. So we have hyperbolic structure, so we can consider Chern-Simons invariant, and then so Boole conjecture is like this. So the Kashaev invariant grows exponentially, and n goes to infinity. Kashaev invariant goes to expands exponentially, and if we calculate this value, and then that gives Boole Chern-Simons invariant. But that is Kashaev invariant. People usually change this one as convergence polynomial, but same one. And for this one is actually proved for figure A not, that this one is definite one. And then 5 to not. So although it is proved, it is proved by Kashaev and Yokoda, but they didn't write down the result. So, but there's some hand script that actually proves for 5 to not and twist not, but those are not yet published. And for that case, that's all. When you figure it out, that's all. Because the Kashaev invariant is really complicated. And so it is very hard to calculate the left side. Yeah.
What about the threshold?
Triple is not hyperbolic.
Yeah, but you should get 0.
Yeah, in the case, yeah. And a little more. So if you consider the volume of torus knot 0, then it is proved for torus knot and a little more. And the main difficulty of this conjecture is calculating left side. To calculate right side is, now we have lots of tools, so it is kind of easy, but calculating left side is difficult. But when Kashaev suggested this conjecture, actually he considered other types of limit. So in his article, it is not vague that he actually considered the actual limit was some kind of other types of limit. So I will explain other types of limit, and that is very easy to calculate. So assume there are several assumptions. Assume only one term dominates a limit. So it looks a little vague, so I will write down what exactly this means. Now, fix the expression of Kashaev invariant. It should be expressed by magic variables and then product of R matrices I7, I8, I5, I6. So type the product of R matrices and extra terms. And consider the limit. Pi over n log. So actually, Kashaev invariant of summation of those terms. But assume that we can ignore the summation. If we put out the summation, only one term grows really fast if n goes to infinity. One term grows really fast compared to other terms, and assume that term determines the limit. And then we can, if we can find that term properly, and then we can write down this way. 2 pi over n, and then inside becomes log r, I3, I4, I1, I2, plus log r, I7, I8, I5, I6, plus log extra term. And if we see the extra term carefully, and then this will actually converge to 0 as n goes to infinity. So what we have to consider is just those R matrices. For certain, so if one term dominates everything, then there should be there's the index that dominates everything, and then for that case, we can express this way. So this one is just hypothetical idea, but it actually holds for figuring that case. And then there's very interesting fact of those quantum integers that if n goes to infinity and so if n goes to infinity, then quantum integers actually behaves very nice. 1 over qi. This one actually goes to the logarithm qi minus pi square over 6. And q inverse I goes to pi square over 6 minus the logarithm q minus I. In here, the logarithm is defined by this way. It's defined by contour integral log 1 minus t dt. This one is called Euler logarithm. The logarithm function appears a lot in the calculation of volumes, and it has really close relation with volume and Sassano invariant. And so quantum integer, if n goes to infinity, actually quantum integer goes to the logarithm function. So if you apply those philosophy to R matrix itself, and then we can express R matrix as logarithms. If n goes to infinity, then we can use those ideas. Before go further, I have to remark that the logarithm function is multi-valued function, so it depends on the branch of logarithm. So we have to handle the branch well for the logarithm function. And so anyway, now we ignore the branch problem, and then if we formally consider the consider this logarithm R by the KN. And then if n goes infinity, and then we can express it like this way. By logarithm Q I minus 3, the logarithm Q minus 3 minus n plus logarithm Q L minus K minus 1 minus logarithm Q minus K minus I.
If you have I divided by n, then I goes to infinity this time.
Yeah, I also goes to infinity.
Yeah. But the other side was to the I. So that infinity.
So Q to the I actually is converges to constant, because Q equal exponential s root of unity and I. So if you consider, this one goes constant. And I will cheat here. So n goes infinity, so sometimes a real simplifying is okay. So I leave minus 1. I think that doesn't make any serious problem. And then, so instead of calculating Kashaev invariant, now we will consider this logarithm function. Logarithm is very nice function and it is very easy to handle. And we consider kind of analytic continuation of R I Z K L. So Q is S root of unity, and so those values actually are all, the actual value of all these values are actually 1. But we extend it a little bit by just formally substituting Gi as Qi. So you can see many parts are artificial and we assume too much several cases. But if you see the optimistic limit and then everything goes very well. And so I feel that this direction is right. So with those ideas, I will explain optimistic limit. In here, we calculated Kashaev invariant roughly, and in here we use those substitution. So instead of I1, I2, I will denote this one as G1, G2. So I will change those G variables. I will use G variable directly. G3, G4, and then G5 here. And then here G6, G7, G8. And for G9, 10, 11, actually, if you see the definition of local maximum and minimum, those values, G9 is actually G2 plus 1 or minus 1. But it's just a little different. So we denote that just G2. If n goes to infinity, we can do that. And then in here, G5 is here, G1 is here. And then using this philosophy, consider the R matrix. The variables are assigned Gi, J, Gk, Gl. In here, then if you apply, in the case, if you see that formula, and then you assign those functions for this partial crossing, minus Gl, Gj, plus by logarithm Gl, Gk, minus by logarithm I over Gk. But this function comes from the I matrix. And then for negative crossing, in here, actually I didn't write down the exact formula of R inverse, but there's you can easily find the formula. And then if you apply the same idea, it becomes like this. Plus logarithm J over L minus plus it looks like this. So for each crossing, we can assign those logarithm functions. And for figuring out, we define potential function by adding those logarithm functions. So in here, for example, in this case, first crossing gives logarithm G5, G1 minus logarithm Ga over G1 plus logarithm G8 over G6 minus logarithm G5, G6. This one comes from the first crossing. This one gives this function. And then we have other terms. And then final case, we have negative crossing. So if I apply this formula, then final crossing gives G4 over G1, G3 plus G4 over G2 minus G1, G2 plus by logarithm g1 over g3. So this function defined almost combinatorial. From the diagram, we can easily find this function. And this function is called Yokoda potential function. So actually, Yokoda potential function is a little modified here, from here, but we changed it a little bit, and I think this one is more natural. And this function has really interesting properties a lot. So, of course, this function depends on the diagram. And the idea is to find maximum value of V. So this function, V function, actually has all the information of Boltzmann and Simon equation. And actually V has all the information of hyperbolic structure. That is very interesting. So to find maximum value of V, so by saddle point, so consider certain function has maximum somewhere. And then the function, if that function is differential function, and then its derivative should be 0. So we want to find those saddle points. So let H be the set of partial derivatives of G. S is solution of H. And then we divide it as Sj. Sj is has connected component. Sj is C1s connected component of S. So we consider a solution set, and then we divide it by has connected component set. So we added C1 for technical reasons. And we assume assumption that S is not empty. So if S is empty, then there's nothing we can do. Assume S is not empty. And if you actually calculate, then most of the time S is not empty. Actually, S has so many solutions, literally infinitely many solutions. And then in this setting, we modify the function a little bit. So actually, if you see this one, this H solution, so solution means kind of saddle point here. So the solution actually makes this value 0, the partial derivative 0. So it is actually saddle point. So we want to find, it's kind of a way to find maximum value of V. And then we slightly modify V to V0. This one is kind of technical reason. Minus. So for usual potential function V, we add a little controlling term, or just one. And then we find very nice properties. Then lemma 1. For a solution of H, so if we pick an element in S, and then so usually the logarithm function is really hard to handle. But if we modify v to v0 like this way, and then the result becomes independent of the choice of branch. So this one is very nice because the logarithm is really difficult to handle because of the log branch. But if you consider v0, and then there's no problem. And lemma 2. So if we pick an element in one path-connected component, and then this V0 function, so V0 is independent of the choice of branch, this one actually becomes constant. And of course, it should be valued of the pi square. Of course, if we change the component, and then the value changes too. But if we fix one path-connected component, then the value is constant. So very natural question is what is the value? What is the constant? And the result is that value is actually Boltzmann and Simon value. By the way, this V0G is called optimistic limit. So if you see the definition of V0, then it depends on the diagram and also depends on the choice of Sj. But I conjecture for a good choice of diagram and path-connected component, the limit n goes to infinity for the n log. This one actually goes to V0. So there are some ambiguity there. We have to choose diagram well and choose solution set well. But anyway, if we choose well and then the result coincide, that is conjecture. And there is some evidence that V0 actually determines Boltzmann and Simon invariance, so it is very natural. This definition, definition of V0 actually comes from the R matrix and certain ways, so it looks kind of natural. Proposition is that we define H. Where is H? H is here, It's a set of equation. H becomes hyperbolist equation of Yukoda triangulation of S3 minus so for link complement we can usually define triangulation of link complement, but in this case we add 2 more points and then we remove 2 more points, so it's not standard way of triangulate hyperbolic manifold. In some ways, this one behaves very nicely, and so it gives certain triangulation of non-complement minus 2 points. And those 2 points actually regular neighborhood of those 2 points becomes just a rule. So that is kind of redundant point, and we can actually collapse the point to 1 point, and there's no problem. So, and hyperbolist equation actually consists of Solution's glue equation and cost condition. So Solution's glue equation actually corresponds to the condition that the result becomes manifold, and cost condition means completeness. So those two, I call those two conditions as hyperbolist equations. So H actually determines geometric structure of certain triangulation. That is very interesting because while we define H or V, we didn't use any triangulation law. We didn't use geometry, but we have relation with geometry like this. So as a corollary of this fact, if we choose a solution in S, and then maybe I will write. If we choose such a solution, it induces a parabolic representation OG that comes from S3 minus 2 points to TSL to C. This one is isomorphism of hyperbolic space. But interesting fact is that actually this one is same with just link complement. So actually the solution, this G is a solution of hyperbolic equation of non-complement minus 2 points, but actually it induces representation of non-complement. That is very interesting, right? And there's a formula for volume and Simon invariance for those representation. So here, this one is from me and my advisor, Kim, and his student. Actually, before proving this one, I studied optimistic limit with Yukoda and Junrakami. Wrote many aspects of optimistic limit with them, and then now I find kind of definite return, the most natural return using those. But many ideas are based on their code. So theorem is that for hyperbolic link, and V is Yokoda potential function. And assume S is not empty. And then for solution V0 G actually becomes -1 volume of that representation plus -1 Simon invariant of that representation volume 80. Furthermore, there is certain G in S that satisfies V0. G0 actually gives -1 volume, hyperbolic volume, and this is the result. So for each solution, it gives the volume and Simon invariant of the representation, and especially there's certain solution that gives hyperbolic volume and Simon invariant. And idea of proof is so I used extended block group theory. Zicker's formula is useful for calculating volume and Simon invariant of representation, and they use extended block group theory. So I applied their theory and then to obtain this. And then this one is kind of correlated from previous picture.